Okay, hi, I'm Greg Favor. Today I'm going to give you an overview of the RISC-V RAS error record interface standard that was ratified earlier this year. Okay, let me first, though, define what is RAS, which is really an acronym that represents reliability, availability, and serviceability. Reliability is about a system maintaining correct operation on an ongoing basis, which includes recognizing or detecting faults or the errors that result from faults as they occur and handling those in a suitable manner so as to maintain correct system operation. Availability is then about kind of a measure of the tolerance for errors, since they will occur during normal system operation. And that involves various techniques such as error correction, error containment, having redundancy, a variety of possibilities depending on the system design. And then you have serviceability, which is about time to restore service back to correct operation. The RERI standard is really more having to deal with the first two things. And really about the logging and reporting of errors. And essentially, it's trying to standardize that framework. And I would emphasize the word framework, since the RAS needs of systems can vary widely from one system design to another. And so again, this is providing a standard framework that a system designer can employ in their system. And again, this is focused on two things. One, the logging of information about errors that have been detected, and then about reporting those errors to system software. The RERI standard itself essentially amounts to sets of memory map registers that record various information about errors that have occurred. Oftentimes, that would also include things like being able to count the occurrences of corrected errors. Yes, they were corrected, system operation continued on normally, but oftentimes you want to keep a count of those, because if that count starts getting high, that's probably an indication of a looming, more serious error coming, and it gives an opportunity for system software to be maybe more proactive about that. The RERI standard also does include support for what's called error record injection for being able to test your RAS handling software. First, before I get into the heart of things, it's worth just establishing a common terminology. And this all starts from hardware faults, which then manifest as errors that result in corruptions to system state. Maybe it's corrupted tag or data in a cache, or in DRAM, or in a bus, et cetera. And then you can start categorizing or classifying errors as is shown on the right. First, between detected errors and silent errors. Silent errors are particularly bad, since then the system thinks it's operating perfectly fine, yet bad computation is happening and totally unaware to the user. So certainly something to be avoided. And so we'll focus on detected errors. At which point then you can break down into errors that are correctable and are in fact corrected, versus uncorrectable errors. And then in the case of uncorrected errors, you have an interesting option in many system designs to defer some errors. A common example is you detect the data of a line of memory, whether out in DRAM or in a cache, as now corrupted and uncorrectable. It doesn't need to immediately impact system operation, because no one's trying to use that data yet. You may detect that's corrupted. What you can do is what people would call poison the data, which is basically apply a poison marking to that data, so that as that cache line travels around through the cache and memory hierarchy, it's maintaining that marking, and then it's not until some processing agent or some DMA or IO agent tries to consume that data, then you have more serious matter, and that deferred error now becomes a critical error. Also, there's other errors, like say a corrupted tag of a cache line that is kind of serious right then and there, and that immediately becomes a corrected error. And ultimately then, when you have corrected errors, there's also then the matter or further classification of, is it containable in terms of the impact on the system? Is it the whole system, or can you contain that error to maybe just a part of a system? Or is it just not containable? Which is obviously the most serious thing in terms of you're probably looking at rebooting a system at that point. And so the RAS error record interface standard draws distinctions between corrected and uncorrected errors, between deferred errors and critical errors, and so on. And that's part of the information that it records when it logs errors within the RERI registers. Okay, this gets to the heart of the RERI standard. And RERI is really standardizing the middle part of that diagram at the top. It's also worth noting that the RERI standard provides a lot of flexibility to a system designer in terms of what components are in the system that have the ability to detect errors, and however they detect them, how do you want to associate those components with what is called error banks? Maybe each component at very fine granularity has its own dedicated error bank with some number of error records, or maybe you have some degree of sharing of error banks between components. Complete system designer choice. But in any case, you have components in a system that, let's take a concrete example. Maybe you have a particular cache inside of a RISC-V heart or CPU. And you might choose to have an error bank associated with that cache. And you might have maybe a few error records, maybe one error record is dedicated to logging tag errors, another for data errors. And, but again, there's a lot of flexibility of how you can use the various records within an error bank. But what I just mentioned is sort of a typical kind of example. And so a given error bank has a header and then some number of actual error records. The header has information to identify the nature of the component it's associated with, as well as indicating how many records are in that error bank. And then you have the error records themselves, where each error record can log a complete set of information about the occurrence of an error. And again, oftentimes, different records are associated with different subcomponents of the component. The other part of RERI is, again, there's the logging part, and then there's the signaling or reporting part, where RERI provides standardized support for configuring on a per record basis how that signals the occurrence of an error that's been logged to system software, such that you can draw distinctions in terms of the severity or the priority of the error. Okay, an error record itself contains a set of registers, and again, these are all memory mapped registers, all contiguously mapped registers. And there's one control register that has various fields to configure and enable the logging of errors and how logged errors get reported or signaled, as well as support for error injection and some other things. And then you have a set of additional registers, starting with the status register, that records information about a logged error. The other registers is this recording further information about it. The idea is that between that set of registers, you have one fully self-consistent set of information about an error. You don't have a mix and match of if multiple errors have occurred over time, some registers reflect one, others reflect another. You have one consistent set. On a later slide, I'll talk about, well, what happens when over time you have multiple errors that occur. I'll come to that. But at any moment in time, you have a complete self-consistent log of a whole variety of information about an error, the nature of the error, where it occurred. There's a lot of optionality, again, to give flexibility to a system designer in terms of the type of information and so on. And again, support for corrected error counts, et cetera. Okay, now this comes to what I was just mentioning a second ago, that you have a component or maybe a subcomponent with an associated error record, and over time multiple errors occur. The first error, you logged it, and then another error occurs. What do you do? And the general idea with the RERI standard is that higher severity class errors will then, they will get logged in place of the existing log. You'll overwrite the existing log with a new log of information. And we'll also record that not only information about this higher severity error, but also the fact that there had previously occurred a lower severity error. And if you have multiple errors of the same severity, again, you're going to keep the log of one of them, and again, you'll note that multiple of these have occurred. So again, we're trying to maximize the information that can be provided to a RAS handler at the end of the day. About not just, here's one error log, but what all has occurred along the way since then. Okay, one thing that the RERI standard supports is the testing of RAS handling software, RAS handling system software. And it starts from a point that it can be very hard to deterministically set up RAS errors in hardware, and all the kind of possible errors and the possible scenarios and so on. So this isn't about trying to exercise or test the hardware detection mechanisms. That's very system specific. This is about providing support to be able to test the whole software infrastructure for handling RAS errors. And so the idea is that test software can come along and it can set up an error record within a bank, configure how it's going to be signaled, although it won't be signaled right away. And then it'll set or configure an error injection delay counter that'll start counting down. And then presumably this has all been happening during normal system operation. We've set up this error that then, when that counter counts down to 0 sometime later in the middle of normal system operation, just like what would normally happen with a real error, asynchronously, the error gets logged. In this case, the log is already sitting there, and now it gets signaled to RAS handling software. And again, in the context of normal system operation, not within the context of a special test environment or test setup. So that's the general idea of this support. And lastly, from a software perspective, this reflects a Linux-based environment. And RERI very much leverages existing software standards, not only just general RAS frameworks within Linux, but also the support through UFI and ACPI. And I'm not going to walk through the diagram, but this kind of just reflects that there's various layers of system software, again, corresponding to these various standards, which starts from down at the hardware level, where RERI is playing to simply capture or log the information about detected errors, and to then signal them to, in this case, a part of UFI to then turn that into sort of software records that can then be passed up to other layers in the overall framework. And just to summarize, that, how do I want to say, RERI, as part of its flexibility, very much strives to also be applicable to the wide range of components. It's not limited to CPUs or memory controllers. It can be I/O agents, you name it. And where it gets applied is, again, a choice for a system designer. And just jumping to kind of the bottom bullet, that this coexists with other RAS frameworks, like say for PCIe, which has its own standardization of error handling. RERI doesn't say that everything must be, follow the RERI standard. You can mix and match as makes sense in a system design. And so as I've covered, that RERI is just trying to standardize the logging and the reporting of errors through a set of memory map registers. This all then configurable in terms of how that then gets signaled to system software. And the other thing, which I've kind of been touching on, but just, it's worth emphasizing, that not only is there a lot of flexibility, but very consciously, there's a lot of room kept in the standard to allow for future extensibility. Such as, for example, if one was looking to address like more automotive applications with functional safety, which have much more extensive RAS requirements, that there's a lot of room for extending the RERI standard as sort of a base RERI architecture to address the additional requirements of, for example, functional safety. And that is it. Any questions? I still have about 3 minutes left.
I'm pretty interested in the error record injection. And you mentioned two things. I'm interested in the error injection. Two questions. One is, you said you can set things up so at some point in the future the error will be signaled. How is that measured? Or is it not defined?
And by measured,
you say
the time delay?
Yeah.
I'm forgetting exactly, but I believe it can be counted clock cycles would be the typical thing. But a system designer can choose to be counting, well, again, like what frequency of cycles. There's a lot of flexibility,
Yeah.
but essentially you're counting some form of clock cycles.
Okay, or it could be retired instructions.
Yeah.
Okay.
Yeah.
And the second part of that is how exactly is it signaled? Is there a dedicated interrupt?
Yes. Well, and thanks for reminding me. I should have pointed this out. That, again, it's part of this idea of providing a lot of flexibility. System designers want to do different things. A common thing is, what are these reporting signals? They're interrupt request signals in many systems. We're not forcing that be the case. Especially when you get into more sophisticated applications, signaling an error may not just be like a 1-bit like interrupt request signal. There may be some other bits of information to go with it that feed into some network that's gathering all these RAS reporting signals from components all around the system and maybe categorizing them and prioritizing them and so on. And again, some of this can possibly arise in like functional safety applications where you have to very quickly react to errors, and you have error banks all over the place and so on. And so again, that's why signal is sort of an abstraction. But for most of us, it's an interrupt request signal. Any other questions?
Yeah. So this is a bit of a dumb question. I don't know very much about RAS. I see that all the counters are corrected error counts. What happens to the uncorrected errors? Do they never have to be counted? I just don't know.
Well, in short, they aren't counted since they get dealt with right then and there, meaning either they can be deferred through a poisoning or they're serious critical errors that need to be signaled and dealt with right then and there. The idea with correctable errors is, yes, they'll get logged, but since we're able to correct the error, system operation continues on. There's no immediate need to inform system software. Now, that corrected error counter can be configured that, hey, the first time that you have a corrected error, you're going to immediately signal that. It's just a matter of configuring that counter. Or you might say, hey, system software only wants to hear about this after there's been 100 corrected errors. So that's kind of what's happening there, is that these uncorrected errors really need to be signaled right away. These corrected errors, system software might want to not be signaled on every single one, only when there's been a bunch of them.
Thank you.
Any other questions? Okay, one last question. Yeah.
Looking to the future, what do you see? I mean, do you see an extension of these things, for instance, addressing specific requirement from functional safety standpoint?
Yeah, no, good question. And as is true with most RISC-V standards, especially kind of new ones that sort of establish some base standardization. They don't try to boil the ocean and address all possible needs, but try to establish a base standard. And then it's up to interested parties to come along and say, hey, we're interested in developing some further RAS standards for FUSA applications. And then those motivated parties interested in that would then form a task group, et cetera. So it's really membership driven. Okay, thank you.